film was attempted by him in 1993, Professor Arun Majumdar, and in the case that the distribution function there is not explicitly used, but he defines a moment of this distribution function called the intensity, okay. And based on this intensity he solves the Boltzmann transport equation in terms of the intensity of what he calls as phonon radiative transport. So, he coins a name called EPRT, equation for phonon radiative transport. It is nothing but the same Boltzmann transport equation, the relaxation time approximation, and cast in terms of intensity of phonon transport, okay, the phonon radiation. So, that is written in terms of F equilibrium. So, he uses a numerical technique and he solves this as one dimension. Use a simple finite difference is okay. Finite difference should give you a solution, but what is important is we have seen these distribution functions are not only function of physical position, just one dimension. It is not just a function of x, but also function of, for example, polar angle theta. Okay. So, you have to also solve this in theta space. So, you have to therefore numerically discretize your physical space as well as your spherical coordinate space. The physical space meaning your x here, and also the directional space, which is in terms of theta. So, you have to discretize this into discrete number of directions between theta going from 0 to pi and phi going from 0 to 2 pi. Phi is anyway it is going to be uniform in terms of phi, that is the assumption of one dimensional transport, and then use the finite difference method and solve this numerically. The integration can be done by using a trapezoidal rule or any standard numerical technique, Simpson's rule, that should work out. And if you take a higher number of grid points, okay, now, so if you discretize it in a very fine manner, you will be able to accurately match it with the analytical solution. So, I want you to write this program to do that. The reference is the paper by Professor Arun Majumdar 1993. I think it appeared in Journal of Applied Physics, if I remember right. So, the title is something like equation for phonon radiative transport, and it talks about basically writing the BT in terms of intensity, solving that numerically and getting the solution for different Knudsen numbers, okay, from Knudsen number of 0.001 all the way up to Knudsen number of 100, where it is a ballistic transport. So, you simply get a big discontinuity at the boundaries and then you have a horizontal line. So, we have looked at that kind of a solution before. So, he talks about all this. So, I want you to write this program all by yourself. So, you can use whatever programming language you would like, whether it is Fortran or C, C++ or in MATLAB or Python, whatever you want to use. Okay. So, it is not that difficult, it is only basically two dimensions, one physical coordinate, the other is the directional coordinate, right. So, you should discretize them, use some method to calculate the integrals, and therefore solve it for temperatures and plot the temperature distribution as a function of Knudsen numbers. So, by that you will understand exactly whatever we have done. I am giving you some analytical solution. So, how do you actually solve the BT for more complex cases? Then you will be able to know the procedure and compare it with this kind of simple solutions. All right. So, tomorrow let us work on the remaining part of this transport equation, try to find some simple solutions before we go on to the micro scale part. So, therefore, we started off from the BT again. We have made some approximations, and again we have derived two sets of BTs one for the case where transport is parallel to the film, and for that case we saw the F equilibrium is in the direction where the transport happens. Okay, in the case where you have a coordinate system where the transport is happening in this direction, your equilibrium distribution varies in that direction. Okay. Whereas, if you look at the perturbation from the equilibrium, so this is an indicator of the non-equilibrium. So, this non-equilibrium, if it also happens along x, so there is no size effect, because the film is confined in this direction perpendicular to the transport direction. So, therefore, in order to bring the effect of this dimension onto the transport, the deviation from equilibrium should vary as a function of y and not as a function of x. The reason is that now, as we know, if you take at this particular point, so you have the phonons which are basically scattered from all directions, right, and falling on to this point, and similarly they are scattered out. So, there is phonons which are coming to this particular boundary and they are scattered by the boundary. So, as you see that these are direction dependent, and each of these phonon, if you physically track the coordinate, each of this will actually come from different points along x, right. So, they will be originating physically from this point and then they propagate in that direction and they reach this boundary. Similarly, from another position, another set of phonons in a different direction will reach the same point on the boundary. So, therefore, you see that these phonons are carrying information which are now basically showing a variation along x. Okay. So, that goes and scatters, and therefore, dg by dy contains the information of the confinement is this. So, basically you have there is a change in the equilibrium distribution function along x, and now since it is also direction dependent. So, this information is conveyed to during the scattering of the phonons from the boundaries, and therefore, there is a gradient now set up in also the vertical direction for the deviation from the equilibrium. So, dg by dy now will start varying, right, along y also. So, this is now going to carry all what we call as size effects. Similarly, the transport perpendicular to the film is quite straightforward. So, you have transport in this direction, therefore, the equilibrium function varies in that direction, and also the deviation from equilibrium will also be dominant in only the y direction because of the confinement. Okay. Therefore, for that you have only all the derivatives with respect to y. So, therefore, we first started with the transport parallel to the film. We separated out the terms which are functions of y. These are the most important terms, that is we have to solve for g basically, and all the terms with respect to F equilibrium we retain on the right hand side, because these are the functions which are known. F equilibrium is known whichever distribution function you take, okay, and you can therefore find out the derivative with respect to x and Vx, right. Whereas, what we need to know is solve for g, which gives you the non-equilibrium distribution. Okay. So, therefore, S naught of x can be written, for example, the case of charge transport, it comes out to this particular form. So, the variation of F equilibrium with respect to x is coming from the dependence of the Fermi level on x, okay, that is this term, and the other term is the variation with respect to Vx, the momentum coming from the variation of E on that. So, therefore, we have two terms, one with respect to the variation with respect to the momentum, the other with respect to the physical space. Is that clear? So, therefore, this will be your term which is a function of x and which is known. Okay, if you know dEf by dx, you just simply substitute it, you know the electric field, you can substitute it, you know the variation of dF equilibrium by dE. So, now what we can do is solve for G, which gives you the non-equilibrium distribution function. So, as we saw that if you solve for G, the full solution becomes G of y plus S naught is equal to this. Now, this is a function, therefore, G is not only a function of y, but also a function of theta. Okay. So, it is carrying therefore, both the directional coordinate as well as the physical coordinate. So, if you want to break this down into the transport of electrons going in the positive y direction and the negative y direction. Okay. So, therefore, if you look at the top boundary, for example, the top boundary is going to scatter whatever electrons come to that boundary, all going in the negative y direction. So, therefore, the direction cosine for this will be negative. Okay. So, the theta in that case will be varying from pi by 2 to pi. So, the pi by 2 to pi will contain information of all the scattered phonons in the downward direction. Okay. And similarly, the phonons reaching the bottom boundary will have phonons scattered to in the positive y direction. So, there the theta will vary from 0 to pi by 2 and the direction cosines will be positive, right. So, therefore, at every point we can break this G into a positive G and negative G, because we have only transport in the y direction. So, which are going in the positive y and scattering in the negative y. So, we can actually divide therefore, this G into G plus and G minus, right. And therefore, I hope you could follow till this point, right. And you know your azimuthal angle phi is varying from 0 to 2 pi. So, this makes this distribution symmetric, right. If you are solving from theta 0 to pi by 2 and then you are rotating from phi 0 to 2 pi. So, you are going to get the same distribution with respect to theta in the other side also. So, therefore, we do not have to really bother about what is happening to the distribution on this side. Okay. So, on this side this distribution is going to be just simply similar to this. Your theta, your phi is going to rotate this and make it a symmetric distribution about the vertical axis. I hope you understand this. So, therefore, the most important directional coordinate will only be theta. There will be only a variation with respect to theta and not with respect to phi. Okay. So, therefore, now knowing this, so we can have two solutions. So, therefore, the solution can be written as you have a G plus, which is a function of y, and the directional cosine mu, which is nothing but cos theta. That is the cosine which it makes with respect to the vertical axis, right. We have theta with respect subtended with respect to the vertical axis. So, that will be your directional cosine, and in the general solution we had a constant. So, we will write this as C1 exponential minus y by tau into V into nu. I am writing my cos theta as mu minus S naught, and similarly my G minus will be another constant C2. Okay, this constant is going to be different from this, because this corresponds to the distribution going in the positive y, and therefore, I give a plus sign. So, this constant is going to be different for the scattering going in the downward direction, but the other terms will remain to be similar. So, why we are writing this in terms of two functions? It is actually one function, but we have identified a positive y and negative y is to apply the two boundary conditions, because we have scattering from the top wall, scattering from the bottom wall. Okay. So, they are going in certain direction, from the top it is going down, from the bottom it is going up. So, therefore, it is convenient to break this into two distribution functions at every point to find out the constants using the two boundary conditions. Okay. So, if you apply the boundary condition at y equal to 0, okay. So, what kind of a boundary condition can we apply? Now, that is the next important question. So, the one that I have described here, okay, is a case where you have a particular phonon or electron which is coming in a direction like this, for example, and this is getting scattered in so many different directions. Okay. So, there are two extreme cases of scattering. So, one is called diffuse scattering. So, in this case, you can imagine this boundary to be quite rough. So, any incoming electron or phonon will get uniformly scattered with the same magnitude in all the directions. Okay. So, you can draw the length of these arrows uniformly to represent they are all of the same magnitude. So, this is quite similar to your radiation transports. In radiation also you have a particular intensity of incoming wave which hits the boundary and can get scattered or reflected. So, we have two different kinds of reflections. One is a diffuse reflection where the intensity of the reflected beam is uniform, the same magnitude and uniformly spread over all the directions. Okay. This is similar to the diffuse scattering we are talking here. The other is specular. Okay. You can imagine the surface to be very smooth like mirror finish, and therefore, if a particular electron or phonon comes and makes an angle theta I, this is your incident angle. So, it gets reflected such a way that theta r is equal to theta I, and it gets reflected only in the same direction. Okay. So, therefore, this is a completely different kind of a boundary condition compared to this. So, in other words, this is a kind of a boundary condition where any non-equilibrium distribution function, if it encounters a diffuse interface or diffuse boundary, will get converted into a equilibrium distribution function which is uniform. Because what is the characteristic of equilibrium distribution function? It is uniform with respect to directional space. There is no variation, only you have a variation with respect to the physical coordinate, but not with respect to directional space. Okay. So, when you say F equilibrium is not a function of theta and phi. Okay. So, therefore, whenever your phonon distribution function encounters a diffuse interface, your non-equilibrium distribution F will become equal to F equilibrium because it is uniformly scattered, whereas in the case of specular it is not so. Okay. So, therefore, to apply the boundary condition at y equal to 0 that is at the bottom surface, our F will now become equal to F equilibrium in the case of diffuse scattering, and therefore, this will tell that G will be equal to 0. Okay. So, these are two extreme cases, the real surface will be a combination of both of them. Okay. So, similarly at y equal to let us say D, this is at the top boundary, again your F will be equal to F equilibrium and therefore G will be equal to 0. So, now when we are saying this G here, what does it indicate, G plus or G minus? The first one at y equal to 0, G plus, okay, and here G minus. So, we can therefore put this in the corresponding distribution at y equal to 0. So, we will be using, let me call this as 1 and this is 2. So, at y equal to 0 we will be using 1. So, can you substitute and let me know what is the constant C 1? S naught. So, you have C 1 is equal to S naught from the second boundary condition. Your C 2 turns out to be S naught e raised to d upon tau v nu. Therefore, if you substitute this in terms of G plus will become S naught into exponential minus y by tau v mu minus S naught, okay, and we have G minus which will be S naught exponential d minus y by tau v mu minus S naught. We will call this as equations 3 and 4. Is that clear? They are substituted for C 1 and C 2. That is it. Now that we know the equilibrium non-equilibrium distribution functions in the positive y and negative y, all we need to calculate what is the flux of the charge. So, how do we do that? We already know how to do this, right? So, let us call this as so what is the notation you use for charge flux? J, we used J. So, let us use the same. So, J, which is indicating your charge flux or current flux, how do we calculate it? Do you remember? From your distribution function. You should not even go back, you should just by now know how to do it. So, for a single quantum state, what is the charge flux? Okay, minus E Vx into F per unit volume, and now therefore integrate over all the quantum states kx, ky, kz. So, this will give you ampere per meter square. So, if you convert this, now you know how to convert the summation into integral dkx, dky, dkz, from which you can use density of states, convert this momentum space into coordinates involving theta and phi, correct. So, what do you get in terms of theta and phi? So, we have one integral over dE and then 0 to 2 pi d phi and then we have 0 to pi minus E into V of x f, we have density of states d of E by 4 pi sin theta d theta. V of x is nothing but V cos theta. Is that clear? We already did this conversion before while deriving the continuum equations. So, now all we are going to do is what? We know solution for G, which is nothing but F equilibrium minus F. So, we defined G as F minus F equilibrium or F equilibrium minus F. I think it was F minus F equilibrium, right? F minus F equilibrium, F minus F equilibrium, and therefore, we can write F as G plus F equilibrium. We know the solution for G from equations 3 and 4. All you have to do is break the 0 to pi from 0 to pi by 2 and pi by 2 to pi. So, that is positive direction cosine and negative direction cosine. So, write in terms of G plus G minus. Okay. So, therefore, now J will become minus 1 by 4 pi E d of E, this is over energy, and then we have 0 to 2 pi, it is not varying with the phi space. So, this can be taken out. Now, with respect to 0 to pi, so my cos theta is nothing but mu, right, mu is equal to cos theta, therefore, d mu will be sin theta d theta. So, I can write this as d mu and this as mu, and therefore, my limits of integration will become, if I put cos 0, mu will be 1, cos pi will be minus 1. So, it will be minus 1 to 1. So, I can break this minus 1 to 1 as yeah. So, minus 1 to 0, okay, V of x or V times G plus G minus here, okay, minus 1 to 0 indicates the negative cosine. So, we will use G minus y comma minus nu, this indicates negative 1 plus 0 to 1 V G plus y comma mu, all this d mu, right, into this is d. Okay. So, therefore, all we can do is now what happened to F equilibrium? Integral F equilibrium cos theta sin theta d theta d phi 0, because F equilibrium is uniform in theta and phi direction. So, therefore, if you integrate cos theta sin theta d theta d phi, it is going to be 0. So, now you can substitute for the solution for G plus and G minus. Okay. So, if you do that, I will only give you and also for S naught. S naught we can substitute from here, right. So, if you do that, so you will get a lengthy expression J 1 by 4 pi get E d of E dE 0 to 2 pi d phi and 0 to 1 V into E tau Vx df naught by, I am substituting for S naught here into Ex plus 1 by E df by dx exponential minus y by tau minus 1. So, essentially equation 3, I am taking S naught common. So, we have this minus 1 and S naught I have simply substituted from there. Okay. So, this is from, this is on one half, the other half will be 0 to 1, we have V into E tau Vx df naught by dE into Ex plus 1 by E dEf, again S naught and exponential we have d minus y by V tau mu minus 1 d mu. So, I have one Vx here, so that should become V square. Let me see, did I miss? There should have been a cos theta again extra, right? I think, yeah. So, yeah, but I think this Vx should be there, but there should have been an extra cos theta there, right? So, in the d omega, that is your solid angle, should be cos theta sin theta d theta d phi, correct? So, therefore, there should have been an additional cos theta, am I right? Okay. So, that should therefore, we can write this just in terms of Vx here and just simply continue. Okay. Huh? Yeah. So, that cos theta is mu. So, Vx I am just leaving it as it is. So, Vx is going to be just V cos theta, we will absorb it in the next step. So, there is again one more Vx, okay, where we will again have V cos theta. So, we will have cos square theta there. So, we have Vx coming here and then okay. So, therefore, we will have Vx here. So, we have Vx square, which is V square cos square theta, right. So, that is nothing but V square again mu square. So, we can also write in terms of that. So, can you now rewrite this in terms of mu and try to find out what will happen if you integrate with respect to mu. Okay. So, you have this function is a function of mu and your Vx square is nothing but V square mu square. Yeah. So, we can write minus 1 to 0 as equivalent to minus of 0 to 1
and also
mu.
There is a negative sign with that mu.
Yeah. So, that I think that and this have been observed and got a positive sign here.
Three negative signs.
I do not think so.
Is there and 2 will be
There will be 3 negative signs here.
Consist of cos theta is minus sin theta.
yeah. And we have again changed the limit, so it will be again minus sign.
Yeah, minus sin theta. Yeah, I think, but you are right. This will be again minus sin theta d theta, but I think finally what I work out is you get only a positive sign here. You have to check that again, please. We have to be careful here. Okay, just hold on. Okay, Vx is not cos theta here, it is sin theta, because our notation is, this is my theta, okay, and this is my Vx. So, therefore, Vx will be V sin theta. So, therefore, this will be 1 minus mu square, okay, this is nothing but sin square theta.
Vy is a v,
Huh?
Vy is a v cos theta.
Yeah, Vy is V cos theta. So, in this case we have taken theta to make to be angle with the vertical, right, and our transport is in the x direction. So, that will be V sin theta, and therefore, you will have 1 minus mu square, that is sin square theta. So, please integrate it with respect to mu. Think
Mu will be sin theta, then you will get cos theta for d.
mu will be
Sin theta.
mu will be cos theta here, mu in the sense, now that is the positive y and negative y. So, that will be with respect to cos theta. We have Vx, still I am not completely convinced about my, I think this is okay. Okay, so I think a few more things. So when we write Vx, it should be just a second. So yeah, so let me again clarify this. Your Vx is not simply V cos theta; it is V cos theta. It should be V sin theta cos phi. Okay, because in 3D you are looking at this projection in this particular plane which is making an angle phi. Okay. So, you have to actually look at V cos phi, which is basically this one, okay, and you are also looking at this cosine in this direction. So, therefore, it is V cos phi sin theta, right. So, that is your direction cosine in the x for this case. So, therefore, you also have a cos phi. So, there will be a cos square phi also in addition to this. So, we will be adding cos square phi to this d phi. Okay. And so, this d mu, no, I think now right I mean this d mu is fine. So, we do not have to therefore do anything here. So, I think now things are falling in place. Okay. So, you have to be careful that we are working with transforming theta to mu. So, therefore, our sin theta d theta has become d mu. Okay. And again when we are talking about transport Vx here, so that is nothing but V sin theta cos phi. Okay. So, therefore, we have V square sin square theta cos square phi, and sin square theta we can write as 1 minus mu square, and cos square theta we have as integral 0 to 2 pi cos square phi d phi. So, to just give you, so this integral 0 to 2 pi cos square phi d phi will be equal to pi. Okay. You can evaluate and check this. And finally, so you should so you have a common term. So, therefore, see therefore, we can take this entire term E x plus 1 by E d E f by dx out, and therefore, we can write this as j, and we can bring this to the denominator. So, we have E x plus 1 by E d E f by dx. So, this will be equal to 1 by 4, okay, and we have over E we have E square V square tau, and we have the dependence on E will be through df equilibrium by dE, we have d of E. So, we have a very lengthy expression here. Okay. So, therefore, we have there is an E here and E here. So, we have E square, okay, and we have V square df naught by dE d of E dE. So, this is a term, common term, E of x plus 1 by E dE EF by dx is taken out and to the other side. Okay. So, we have this term here and the others are all dependent on mu. So, we have 0 to 1, 1 minus mu square into exponential minus y by v tau mu minus 1 d mu plus 0 to 1, 1 minus mu square exponential d minus y by v tau mu minus 1 d mu. So, this pi cancels because our integral cos square phi d phi is pi. So, there is 1 by 4 pi and that pi cancels off, right. Now, please go back to our derivation of Ohm's law, what was the expression for electrical conductivity that we got? Which term is it? This term, right? So now, therefore, if you look at it apart from that, we also have this additional terms which are nothing but the size effect terms. Okay. So now if you look at J divided by Ex plus 1 by E dEf by dx, okay, what is this? What does your Ohm's law say? Your J should be equal to electrical conductivity times your electric field E of x plus you have a electrochemical potential 1 by E dEf by dx, right. So therefore, this entire term here is nothing but minus sigma. You understand? So when you divide this current flux by the electric field, this is nothing but minus of sigma. So J should be minus sigma of this. So therefore, this is minus sigma. So therefore, the expression for electrical conductivity now, where we have nanoscale transport, is equal to this, and out of which we obtained that the bulk value of electrical conductivity expression is this, correct? I hope all of you are able to follow. So the expression for bulk value that we have derived, let us go back to that. This is your expression. We have minus E square integral tau V square dF equilibrium by dE d of E d. Okay, we have minus E square by 3. So therefore, we can write this as, we can multiply and divide by 4. Okay. So therefore, what we have here can be rewritten in terms of the bulk thermal conductivity. So this entire term is nothing but your bulk electrical conductivity. Understand? So Je by Ex is nothing but your bulk electrical conductivity. So if you therefore write this in terms of sigma by sigma b, so the expression on the left is nothing but sigma, and what we have is in terms of sigma b. Therefore, we can write directly an expression for ratio of sigma by sigma b. So that will come out to be 1 minus 3 by 8. So I am just using some notation, I will expand what it is, 1 minus 4 times E3 of zeta. So you can use some notation minus E5 zeta. okay. And what is zeta? This is nothing but d by the mean free path, okay, or this is equal to 1 over Knudsen number, okay. And my E subscript n of x indicates integral 0 to 1 mu power n minus 2 exponential minus x by mu d mu. So, all I am doing is writing this product of v tau into mean free path, okay. And then I evaluate these integrals and I leave. I will end up with two integral terms, one which is E3. E3 is nothing but mu times exponential minus x by mu d mu. The other is E5, where I have mu square, mu power cube, okay, mu cube exponential minus x by mu d mu. So, I have to separately evaluate this E3 and E5 integrals. So, and then I get this resulting expression for ratio of sigma by sigma b. Okay. So, therefore, so this gives you the expression for the size effect in electrical conductivity for the nanoscale transport. If your Knudsen number is very small, so what happens to zeta term? Very large, and therefore, this entire term vanishes. So, for the case of Knudsen number going to 0, what happens to sigma by sigma b? Goes to 1. So, it recovers your bulk electrical conductivity. Now, when your Knudsen number becomes very large, what happens? Your sigma will be much smaller than your sigma b. So, this is called the size effect. I hope all of you are able to follow this. Okay. So, we have derived from the first principle using the Boltzmann transport equation, although it is a very tedious process, we saw that, but this is the simplest possible analytical solution for describing the size effects, okay, from which clearly it says that if your Knudsen number, the vanishing limit of Knudsen number, your electrical conductivity becomes your bulk value. For larger values of Knudsen number, your electrical conductivity is smaller than your bulk value. That means, if you make a plot of this ratio sigma by sigma b as a function of Knudsen number. So, it starts from 1 and then goes like this, right. So, this is called the size effect. So, in nanoscale transport, there is a reduction in the electrical conductivity, okay, even for the case where your transport of electrons is along the thin film and you have a confinement perpendicular to the transport. Even in this case, there is a size effect seen because of the scattering from the boundaries. So, this scattering is going to reduce the momentum of the electrons, and therefore, it is going to also reduce the amount of electron conduction. Now, what happens if instead of, so similarly if you calculate also the phonon, if you replace now with these electrons with phonons and you have a temperature gradient in the x direction. So, we have instead of electric field we can have temperature gradient and we have heat conduction parallel to the thin film and we have confinement perpendicular to that. So, in that case you can calculate the ratio of K by Kb, which gives you the size effect for thermal conductivity. It turns out to be, it will be exactly equal to similar expression as sigma by sigma b. You can do this as an exercise and see that. In this case, you do not have any electric field, you have only temperature gradient. Follow the same steps. Instead of electron charge flux, you replace this with heat flux, and you will end up with expression which is identical to sigma by sigma b. So, you have a similar size effect for also the thermal conductivity. So, now the interesting question is, what happens if you use specular boundary condition instead of diffuse? It turns out if you use specular boundary condition, that the ratio of sigma by sigma b will always be equal to 1 for transport parallel to the thin film. Or in other words, specular boundary condition does not affect the momentum of the electrons or phonons, and therefore, even if you have a confinement and if you apply a specular boundary condition, this is not going to destroy the or reduce the conductivities. Okay. So, tomorrow I will show you simply how this happens for specular boundary condition. Okay. So, with that you will be able to understand that this size effect becomes very important in the transport parallel to the plane only if you have a diffuse boundary condition, whereas if you apply specular boundary condition, there is no change in the conductivity parallel to the confinement. Okay. So, we are talking about now all these conductivities which are in the direction of transport, which are perpendicular to the confinement. Now, the other case is where we have size effects in the direction of confinement. Okay. There, irrespective of whether you use diffuse or specular, you will always have size effects, because the direction of the gradient and the direction of change in the non-equilibrium are in the same direction. Okay, irrespective of whether you use diffuse or specular boundary condition, there is going to be therefore an effect of this confinement. Okay. So, this is the most important property of nanoscale energy transport. Okay. So, if you are working at small Knudsen numbers, you will not be even seeing this effect, but at large Knudsen numbers this becomes very prominent. Okay.